Alright, this video contains the solutions for numbers 22 through 26 on your AP Physics C practice test. Number 22 is a real easy problem once you realize what you need to do here. From your calculus training, a graph like this might inspire you to think about, oh, doesn't that look like something that I can take the area under? Maybe you think that, maybe you don't. Let's see what the relationship is. The graph above shows the force acting on an object as a function of time. The change in momentum of the object from time 0 to t is, well, change in momentum, this is the impulse momentum theorem, is equal to, if it was a constant force, it would be force times time. But this is not a constant force, so it's the integral f of t dt. And we can certainly get that area very easily. So the change in momentum is equal to the area under this curve. And that's a triangle that has a base. If we did 1/2 base times height, the base is t, the height is f. 1/2 base times height is 1/2 ft. This is the area of that triangle. Number 23, we have a moon here of mass m in orbit around a planet that's 49 times more massive. And when the moon's at point A, its distance is r sub a and speed is v sub 0. When the moon is at point B, its speed is 5 times that, 5v sub 0. So number 23, when the moon is at point A, right here, the distance from the moon to the center of mass of the planet-moon system is most nearly, well, this is a lot more massive, so I think that center of mass you would expect would be very close to the center of this. So this distance is going to be very close to 49, or very close to the whole RA. So I think that automatically would get us to either D or E. So let's just do that calculation real quickly. So if we take this to be our 0 point for calculating center of mass, then I have 1 over the total mass, which is 50m, is equal to, and then we remember we do position times mass. So the position of that is 0 times m plus the position of this one is at RA times its mass, 49m. So that gives me, the m's cancel out and I get RA times 49 over 50. That's answer choice E. So just like when we orbit around the sun, the center of mass of the Earth-Sun system is real close to the center of the sun because it's so much more massive than we are. And then in number 24, this is a tricky question, I think, because it's not so clear what concept you should be using to get the right answer. And I will admit, I floundered around quite a bit here before I got the right answer. At this point, where we have RA, that distance, we're going to call this RB. Its velocity is v sub 0. When it goes closer, we know that that means it goes faster. Its velocity here is 5 times as fast. The correct concept here is conservation of angular momentum. Remember, angular momentum, if we treat these like particles relative to this, is L is equal to R cross P. And since everything's at 90-degree angles here, that just turns into R times P, or RMV. So I don't have to worry about the cross product because everything's at nice right angles. At least it is at those 2 points, right? Somewhere else in the elliptical orbit it would not be quite that. So we're fortunate that we have those distances here. So let's see if we can figure those out. Here, the mass is the same for, right? The mass is the mass of this. Well, I'll include it in there anyway. So I get RA times m times v sub 0 is equal to, and then over here I have RB, which is what we're trying to find, times m times 5 v sub 0. So that would give me the m's cancel out, the v sub zeros cancel out. So RB is equal to R sub A over 5, or 1/5 R sub A. And that's right here. And if you use that concept, it gets you there pretty quickly. We've got some more angular stuff going on. These are not the easiest questions on the exam, in my opinion, and we should be able to figure these out, though. And there's a couple ways you can do that. I'm going to take a fairly intuitive approach. The bar shown above is pivoted about one end, and it's initially at rest, straight up, in a vertical position, and then it's displaced slightly, so just a little tap, and then it starts to fall as it makes an angle theta with the vertical at any given time, as shown above. So theta is a variable, right? Which one of the following graphs best represents the bar's angular acceleration as a function of angle theta? Well, I actually went pretty, I used an equation for that. I thought about angular acceleration as a function of theta. Well, I used, let me rewrite what I did here so you can see it. This is problem 25. If we want, what do I know about angular acceleration? I know that torque is equal to moment of inertia times angular acceleration. And the torque in this situation, here's the bar, like this. The only torque on this comes from gravity acting on the center of mass, right? So here is angle theta, right, and that's equal to this, right? Those are opposite interior angles, so those are equal. And that's mg, and it's acting at 1/2 that distance. So if the bar were, like, if that distance of the bar were L, then the torque here would be equal to L over 2 mg sine theta, right? Because torque is equal to force times radius, force times radius where it's acting, times the sine of theta. It's not 90 degrees here, and it's changing. So I plug that in over here. And so that means L over 2 mg sine theta is equal to I times angular acceleration. I just divided the I over here. Whatever the moment of inertia of it is, of the bar is, it's about one of its ends, so it would be like 1/3 ml squared, but it's constant, right? And in fact, all of this stuff is constant. So what does angular acceleration look like as a function of theta? It looks like a sine graph, right? It looks like some kind of sine graph because it depends on that angle. Everything else is a constant. So let's look at the graphs. No, 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 and that does indeed look like a sine graph, right? It starts at the origin, would continue, and that's looks like something, but it doesn't look like a sine graph, right? It looks like it could be some trig function, but not a sine graph. So that's how I got to the answer for that one. Number 26 is the one where I took a little bit more intuitive approach. The problem here is they want, if you thought, well, wait a minute, didn't we have theta as a function of this angle, so couldn't we just take the derivative of that and get velocity? Well, you can't use that kinematics or those kinematics relationships unless you have functions of time, right? So acceleration as a function of time is the derivative of velocity, but not when it's a function of theta. So we're a little bit stuck there. It turns out, actually, I think that might get you to the right answer if you did it that way. But let's take a look here, a little bit different approach. So let's think about what's happening. We want to know, as a function of time, what is the angular velocity. So the bar is displaced a little bit, and it starts to go down, and it hits the ground. What I thought is, like, what would happen if I could envision a more complete graph here, maybe that would help me. Instead of hitting the ground, what if the ground weren't there? What if this were just a pivot point and it could swing all the way around? Let's think about like where the velocity would max out. Up here at the top, it would have an angular velocity of 0, right? And then where would it have the greatest angular velocity? Well, it's going to be accelerating all the way because gravity is going to be tugging on the center of mass all the way through here and then all the way through here, all the way to the bottom. So when it's at the very bottom here, that is when we have our maximum angular velocity. So it goes from here to some kind of maximum. And then here, what's maxed out here? This is where the gravitational, if you think about the torque and how that depends on the angle, when we're here, that's when the torque is at 90 degrees. That's where the torque is maxed out. And the torque and angular acceleration are just related by that. This is where we have maximum acceleration, right? And that's also, we're talking about this as a function of time now. So that's maximum angular acceleration. So that's where this would be the steepest. So this is 0, and then it gets to the steepest point here, and then to its maximum, and then here would have it would be steep again, and then back to 0. So I'm picturing something that looks like this. It's 0, it gets to its steepest point here at 90 degrees, it gets to its maximum here, and then to its steepest. So it looks like we're talking about a cosine graph, right? It's actually a upside down cosine graph that's been shifted up a little bit. And we're only going to 90 degrees, so we're just focusing on this part of it. And that looks like answer choice E. So that was pretty tricky. I found 25 not too bad, and 26 I really had to think about that one for a while until I got there. If you got any better ideas than what I did, I'd love to hear about them.